So today, before we start 2.2 definition of limits, remember I had said we're going to try to do little reviews as needed. And I think this is a great time to review what functions in general look like. As you go through calculus, we're going to be working with a lot of different functions. And what would be best for you is to be able to picture in your head real quick what a particular function we're working with actually looks like. So let's start with a little review of some basic functions. Okay? So the first one, did it just click off? Yeah, I moved it. You know, every time I move it, it's just the HDMI cord. It's all good. It's good. It's working. So I'm just not going to move the computer. We'll be fine. All right. So let's do a quick review. Not of what a function is, but I want you to start being able to picture graphs in your head when I say something. All right? So the first one I want to start with is your basic polynomial function. Because when we do get into limits and stuff, it's really going to depend on the type of function you're working with. So it's really good to kind of picture what these graphs look like in your head. Well, all right, we're going to backtrack one level. I'll move it off to the side here. The linear function. You all know the linear function, right? Mx plus b. All right, a linear function, very simple, graph of a line. Okay, what's unique about it? The x has an exponent of 1. All right, so I'm going to put that up there, but I think we're all familiar with that one. So let's move on to the polynomial. First one I want to start with, we're going to go from linear to an x squared function. All right, you tell me, what's an x squared function look like? You know, linear. That's when x is taken to just the first power. It's a straight line. What happens when we make it squared? What do we get? What's it called? You can use your fingers in the air if you want. It's a parabola. Everybody knows the parabola, right? We're going to be working with that one, obviously. That's your basic parabola. These are all polynomial functions. And we can do variations of it. Instead of x squared, if I took x minus 2 squared plus 5, I just scooted it over 2 and moved it up 5, right? All right, so these are all variations of your functions. How about your x cubed function? Again, you can do air drawings. Air drawings. I'm getting it. It's kind of like, right? Okay, there's your x cubed. All right. How about x to the 4th? Anybody want to give an idea? Very similar to x squared. And how is it similar to x squared? Starts in the same spot. But here's what could, now there are x to the 4th functions that look a lot like parabolas. But we can also kind of go zoom, 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 zoom. See that? There's an x to the 4th. I'm going to stop there. I'm not going to keep going. What would be unique, looking at the pattern you kind of see going on now, what do you think an x to the 5th function, what would be something, tell me something about an x to the 5th function that you think could occur. So linear is x to the 1st, right? If it starts down, it ends up. If it starts up, it ends down. X squared is a parabola. It's either both up or when they're negative, they're both x cubed. Starts down, ends up. Negative x cubed, guess what? Does the opposite. Can you see that? There's the math dance. You ever see that little meme? Yeah. Anyway, I guess only math professors share those. So we have that. Just walk around the offices. You'll see stuff like that on our doors. X to the fourth, either both up, both down. So here's what I want you to remember when you're dealing with polynomial functions. Number one, if it's even, the end behavior is the same, right? If it's odd, the end behavior is different. The other thing is how many turns it takes. A linear function takes no turns, right? That's straight. A parabola actually takes one turn. An x cubed would take 2 turns. You getting the idea here? And x to the fourth could take up to 1, 2, 3 turns. Right? I start down, 2, 3 turns. All right, so these are the things that will help you as you move forward in this course, is just saying, okay, this graph, highest power is x to the 6. That means these things. All right, so they're your polynomial functions, and don't worry. When we get to chapter 1, 2, 3, 4, we will get into graphing these in a lot of detail. Right now, I just want you to visualize them. Okay, so that's your polynomial functions. So let's go over some more. Let's do, I'm just going to call these other functions because there's going to be a bunch of them. Now, here's what's nice. I want you, and you'll get this today as you're working through the lab too, get really used to using things like Desmos to help you learn along the way. So if you ever don't remember, you can easily plug these things into Desmos and instantly get a picture. I like Desmos. You got your graphing calculator. I told you this last week. I love the app of Desmos way more than I like my graphing calculator, and that's what I use, either on this computer or on my phone. But again, it'll be really helpful if you can visualize these functions before you go. So when we talk about 1 over x, couple things when you're trying to picture what 1 over x looks like. Well, number one, we got a restriction on 1 over x, right? What's the restriction? X cannot be? Yeah. So automatically, nothing is touching the y-axis, because the y-axis is where x is 0. All right, and if you're ever not sure what these functions look like, start to mentally put some numbers in. So 1 is easy. When x is 1, we have 1, right? But what happens when x is negative 1? What's 1 over negative 1? Negative 1, right? So, all right, we got these 2 points, right? So you should be able to kind of start. And then think about it, oh, well, when x is 2, now I have a half. When x is 3, I have a third. When x is 4, I have a fourth. So it's going to get smaller and smaller. All right. Will it ever touch the x-axis? Can it ever equal 0? No. There's nothing you can put 1 over something that's going to make it equal 0. And then picture the fractions. We got all this space between 0 and 1. If I do, what's 1 over 1/2? 1 over 1/2. 1 divided by a half. 2. Think about it. 1 divided by a half is 1 times 2 over 1. Oh, so here it's going to start, got rid of the whole thing. It's going to look like that. And on the other side, it's going to be the flip of that. So it's going to be the same shape, but it's all going to be negative. So it's going to look like this. So when you have any variation of 1 over x, and that could be 5 over x minus 7 is a variation of 1 over x, it's going to look something like this. Okay? Now, what if I change that function to 1 over x squared? Well, guess what? 1 is still 1, right? We still can't have the 0, right? 1 is still 1. But what does negative 1 become now? 1. So 2 is now becomes it's still a fraction, but it's a smaller fraction, right? It becomes 1/4. So it's still going to have essentially the same shape. It's going to get, sorry. Oh, I will work on that. It just is going to kind of get closer quicker. Does that make sense? And now it's going to do the same thing on the positive. So it's going to look something like that. So there's your graph of 1/x². Okay. Couple more. This course, when you take calculus, if it's a four-year universities have many different types of Calc 1 classes. Four-year university, my daughter went to NJIT, she graduated last year. She was not an art, she was a designer, industrial design, architecture, all those, they have their own special Calc class, okay, where they only do what they need. At the community college, we don't have that. We want you to be able to transfer anywhere, so we give the standard Calc course. Your book says Calculus with Early Transcendentals. Okay, so one of the big things we do that not all schools will do if they have a very specialized Calc course is transcendental functions. Anybody know what they even are? So, transcendental functions, you will see them often throughout this class. We'll start with one you know. Here's a trig function. That's a transcendental function. All right. So know your basic sine graph. It's really helpful. All right. Know the points where your sine graph crosses the x-axis in radians. I know you know them in degrees. Know it in radians. So it's 0, pi, 2 pi, remember that? Know when it's at 1. Well, this would be where? Pi over 2. Or 3 pi over 2. Okay? Knowing that graph will actually help you remember real quick what sine of 0 is, right? What sine of pi is, what sine of 2 pi is. You're going to have to use that a lot. You don't want to be always going to your calculator for that kind of information, okay? Plus, if your calculator's not set to degrees, you get all screwed up anyway. Or not set to radians if you're plugging in 2 pi. So know your sine. Know your cosine function. Cosine function is basically the same wave as the sine function, it's just shifted. All right? So where the sine starts at 0, 0, the basic sine function, we know there's variations. You all took pre-calc 2, you know that thing could be moved all over the place, right? But the basic cosine function doesn't start at 0, 0. Where does it start at? 0, 1. Yes. It starts up there. Same curve. It comes back. Every time it goes away, it comes back. So this time, there's my 2 pi. There's my pi. All right. Again, this is good. It's actually at 0 at pi over 2. Okay. And it's at 0 at 3 pi over 2. Knowing these graphs helps you really quick when we have to go plug in numbers into our sine function, be able to come up with what they are without moving to your calculator. So please know those graphs. The last one, I'm not going to do the inverse, but you should also have a really good idea of what the tangent graph looks like. Okay, tan x. This one was a little different. Remember tan x graph? It is not the wave, right? What does it kind of look like of these over here? Remember, it kind of looks a little like the x cubed graph. You remember your tan graph? All right, your tan graph was different. You actually had asymptotes at negative pi over 2 and pi over 2, and then it did this in between, okay? So what does that mean? If you can't plug pi over 2 into a tan function, it's undefined. Okay, so just remember, tan of 0 is 0. So knowing and picturing the graphs helps you know those functions real quick. All right, the other transcendental functions we're going to do throughout this course. I have 2 more graphs, and then we're going to start the lesson. Again, this is just to help you. You may not see these graphs today. Actually, I have 3 more to go over. The next one, another fun transcendental function. Remember that one? All right, that one you haven't seen since pre-calc 1. If you took it here, college algebra, might not have seen it since high school. E to the x. Okay, what is e? Hmm? 2.7. It's kind of like pi, right? It is a number. It's an irrational number, so we can only estimate it, correct? An estimate, you said 2.718? Yeah, there's a lot more numbers to it than 2.718. That's approximately what it is. You got to think of it, it's a number, okay? Well, so when you're doing the graph of it, you know, if you can't remember what the graph looks like, go with some basics. What's anything raised to the 0 power? What if x were 0? What's anything raised to the 0? All right, I got that. Doesn't matter that it's a 2.718. All right? E raised to the first power is just e, correct? So at 1, it's about 2, it goes up there, right? I'm going to run out of space. I'm going to stretch it out a little bit, but you get the idea. And then what happens on the other side? What if x were negative 1? What happens to e to the negative 1? What does that become? So 1 over e. I'm reviewing a lot of little things here. 1 over e. That's a fraction, which means it's going to get kind of, it looks like that. It never crosses, okay, on my picture, it looks like it does, but it never crosses the x-axis. Okay, because e to the x can never actually equal 0. And because e is positive, e to any x value, whether it's negative or positive, the x value is negative or positive, can never be a negative number. So there's your graph of e to the x. Know that graph. The inverse of e to the x, anybody remember what the inverse of e to the x is? That's a reciprocal function. So there's a difference, that's a good point though. There's a very big difference between a reciprocal function and inverse function. Sometimes the reciprocal is the inverse, okay? E, yeah, yes. The natural log, what makes it the natural log is it has a base of e, where log has a base of 10 unless you define it as something else. And we will review logs a little bit when I get to that point where I feel we need to review properties of logs. Right now, I just want to look at the basic graphs. So ln x. It's an inverse graph. So let's do this one, reminding ourselves what inverses are. So in first, in red, I'm going to put e to the x back on the graph. Okay, and then I'm going to put, I don't know, in green. Anybody know what that is? What line is that? Y equals x. An inverse, if you recall, graphically is a reflection over y equals x. So if you don't remember what ln of x looks like, if you know what e to the x looks like, you can be like, oh wait, it's just a reflection So where we had the point, so remember this point was 0, 1. We said when we plugged in 0, we got 1. The inverse of that is 1, 0. Okay, and this time the graph is going to go like that. So there's your ln x. Right. Yep. So what happens is every point is equidistant. Again, my picture's not so great, but every point is equidistant from the y equals x. Just to remind you of what an inverse graph actually looks like, okay? So I wanted you to just be able to visualize when we throughout the course talk about ln x, talk about it, you can at least picture what the graph looks like in your head. The other thing we touched upon probably very little in pre-calc that I want to review real fast. It'll come back. I have faith that it'll always come back. There we go. Are something called the last one, piecewise functions. Piecewise functions are defined on, it's a different function defined on different intervals. All right, so it might look like this. Okay. How the function is defined would look something like this. So maybe I just want it to be, and I'm totally making this up, but let's let it be just x squared when x is less than 1. Okay? And then it's the graph of x plus 2. When x is greater than or equal to 1. Okay? So that's a piecewise function. What happens is the function is defined as one thing on one interval. So it's a parabola. It's a basic y equals x squared parabola up until you get to 1. And then what happens at 1? It becomes a whole other graph. Now it becomes this linear x plus 2. Okay? What you need to pay attention to when you're, and you will see piecewise functions a little bit today, when you're dealing with piecewise function is what is happening at the split point? Like what's happening at 1? Which function is defined at exactly 1? Yes, you've got to pay attention to that, especially as we go through limits. At 1 itself, it is defined as x plus 2. Okay? The other thing is, when you're looking at how it's written out, when we're talking about minus 1, we're talking about everything from the left, coming from the left, right? When we're talking about greater than 1, we're talking about everything from the right. So that's the other thing I want you to pay attention to when dealing with piecewise functions. Okay? So that is my quick review of graphs. Do you remember a lot of these? I hope so. Okay, my quick review of graphs before we get into playing with limits. All right, so let's move on. I'm going to start with kind of going through some pictures and describing what a limit is, and then we're going to define it formally. But then we do some things first. Last class, we talked about an average velocity versus an instantaneous velocity. And we found we can't technically yet get the actual instantaneous velocity. You can get it when you're driving your car because you got a speedometer in front of you. But what we did is we used the average velocity and made the intervals smaller and smaller and smaller and smaller till we got to the point where we knew what the instantaneous must be. Okay? We used the idea of a limit. So the idea of a limit, you know, if I have a basic, we'll just go with a polynomial function, just some function, right? Let's suppose that is a 3 and that's a 2. All right. These are the easiest limits to work with because we know if this is f of x, well, based on the graph, everybody knows what f of 3 equals, right? Without even me giving you, you don't even need the equation of the polynomial because on the graph, you know what's f of 3. 2. Okay? Not a problem. You've got to think of limits as something different. When we talk about a limit, what we're looking at is, hey, what's the limit? So I'm going to go through some notation now. As x approaches 3. Do you see that arrow? That does not mean equals 3. What's the limit as x approaches 3 of f of x? Now, sometimes, I'm not going to say the majority of the time because the class would be boring if we did that the majority of the time. The limit of the function is what the actual function is at that point, meaning you can just plug it in and you're done. Often you can do that, but that just doesn't make it very exciting. So in other words, if I am going to look at a limit as x approaches 3, a couple things I actually have to do. I have to say, hey, what's happening as I approach from the left? So that's the limit as x approaches 3 from the left. Do you see the little negative sign I put above the 3? That's a new notation you're going to get used to. And then I've got to see, hey, what's happening as x approaches 3 from the right of f of x. All right? If what's happening from the right is the same as what's happening from the left, then you can go ahead. Now, clearly, as we look from the left, the limit equals what? 2, right? It's going to 2. So here's the other thing. The answer to a limit is your y value. You got that? It's your y value. And what's happening as we approach from the right? It also equals what? 2. So if from the right equals 2 and from the left equals 2, then I can just say, hey, guess what the limit equals? That's going to happen on every polynomial. Here's what's great about polynomials. You are going to love working with polynomials in this class. We're not going to work with them very often. They're easy. To do a limit of a polynomial, all you have to do is plug in the number. So in other words, if I gave you a function, right, and I want the limit as x approaches 3 of that function, that's a different, here, let's use a different number besides 3. Because I don't want it to get, let's use 5. Here's what's nice. You now know, that's a polynomial. To get a limit of a polynomial, all I need to do is go ahead and plug it in. I don't need a graph. I can plug it in. But what's that limit going to equal? It's going to equal 2 times 5 cubed plus 5 times 5. All right, we got to do a little math here. We can do this one in our head. Let's try it in our head, right? It'll wake us up. 5 cubed is 125, correct? 125 times 2 is 250. Oh, 270? Yeah, I don't need a graph to verify. It's a polynomial. Polynomials are great because polynomials are nice, smooth functions. They don't have asymptotes. They don't have issues. They're happy. You can evaluate their limit is exactly what the function is at that point. Done. Okay, unfortunately, we don't work just with polynomials. So, hopefully in pre-calc 2, you recall that some functions have holes in them. You remember that? Some functions have holes in them. All right? And let's suppose this hole is occurring at, okay, when x equals 2, the hole's occurring at 1. So, can you define f of 2? Can you actually define f of 2? Is there a value at f of 2? No. The function itself is actually undefined at x equals 2. Now, what does this look like algebraically? This is normally a polynomial function, because this is almost a polynomial function, right? It's almost smooth except for one thing, that hole. Do you recall back in pre-calc what causes a hole in a function? Anybody? What causes a hole to occur in a function? Yeah? Yeah, a fraction. This, but you don't know what this function is. We didn't give it an equation. But I can tell you right now, at the bottom, in the denominator, this has a fraction. And in the denominator, guess what's in the denominator? Go on, try. X minus 2. Because if I put x minus 2, what happens? I can have a perfect polynomial function. I divide it by x minus 2. That function's not defined at 2 itself, right? So that's what happens. That's how you get holes. You're going to see these a lot. But now let's go back to limit. And then after this, I will give you a formal definition of a limit, which I haven't done yet. And this is calc. You're going to do formal definitions and theorems and stuff like that. But remember what we talked about? When I talk about a limit, I don't care what's happening at the actual point itself. I want to know what's happening as I approach from the left and approach from the right. In other words, as I take the limit as x approaches 2 from the left, I'm getting really close to what value? 1. And as I approach the limit, as x approaches 2 from the right, oh, I should have done that in another color. Sorry, that's okay. I'm getting really close to what value? 1. So even though a function is undefined at x equals 2, it can still have a limit. And that's why we work with limits. A function can be undefined at the value itself, but it can still have a limit. The limit exists, even though that didn't exist. Now, there's a lot of different things that can happen. So let's do some definitions now. And the first definition I'm going to give you is the limit of a function. When we do formal definitions, we're going to write everything out. We're going to look at each little piece of it. So and these definitions are also written in the notes. I take them so you have them for you. So let's suppose the function f is defined for all x near a. Does it, remember? It doesn't have to be defined at a. For all x near a. So little pictures help. Here's my a, okay? So all the values near a, my function's defined, okay? If f of x is arbitrarily close to L, so L is going to be that value over there, is arbitrarily close to L, and so arbitrarily means however close we want it to be, okay? For all x sufficiently close to A, we can write that the limit as x approaches A of x equals L. The limit of f of x as x approaches A equals L. Now, this is called a light version of the definition, for lack of a better word, preliminary version of the definition. What makes this a light version? We use words arbitrarily close, sufficiently close. There's a whole chapter. We don't do it in Calc 1. If you were taking the honors course, you can do it. And if you're like thinking I really want it to be in the honors course, you are free to completely read through section 2.7. That is the formal definition of a limit, which actually defines the arbitrary part by using a lot of Greek letters, okay? Like delta and epsilon. We don't do it in this course. So I always throw this stuff out there. Hey, if you're a math major, maybe you want to go and look through 2.7 on your own and see if you can understand that formal definition of a limit. Leah.
Oh, sorry. It says f is defined for, is x near a.
Suppose the function f is defined for all x near a. And again, these are all written out on here, just so you have them. So again, there is a more formal, and what it does is defines how close we get, but we're going to just do it here, and we're going to be fine. And you saw that, and it's very clear. It doesn't have to be defined at A. It has to be defined for values be right near A, all right? But not necessarily at A. So one of the things you do want to be careful of, so I'll give you a little example here. Suppose we have a funky function with a hole there and a hole there. Okay. And then we have a point. So this function has a lot of different things going on. It's got 2 holes in it, and it's got this random point. That's okay. That's a function. What makes it a function? Do the vertical line test. At any point, does it cross it more than once? No. No, because when you're here, right? All right. I exaggerated that squiggly a little too much, but you get the idea. You have one point right there. You don't have that point there. Okay. So there's a couple things that we can do here. And I want to make sure you understand the difference between evaluating the function and evaluating the limit of the function. So what is, everybody, just f of 1? You can kind of see on the graph. F of 1 is just going to be 1. What's f of 2? 5. Do you see that? That's what that little hole, that's a dot up there means. And what's f of 3? Undefined. But that changes if I look at limits. So what's the limit as x approaches 1 of f of x? What's the limit as x approaches 1? So we're like, we're going to approach here, we're going to approach, it's still going to what? 1. Right? What's the limit as x approaches 2 of f of x? So it's kind of hard. Let's make that go to 2. What's the limit as x approaches 2? 2. And what's the limit as x approaches 3? You can see it, right? What's the limit? It's 4. So this just gives you a nice idea of when is a function undefined compared to when is a limit. Right? The limit wasn't undefined anywhere. The limit was fine. Okay? Do you see that? So in the first one, the function value equaled the limit value. We were good there. In the second one, the function value is totally different from the limit value. And in the third one, the function value didn't exist, but the limit value did. Okay? So this just kind of, you got to separate what evaluating the function versus evaluating the actual limit. So evaluating limits. There are 3 techniques that we are going to use. Let me show you one more first before we get into those techniques, because I think this is important. You'll see it throughout the chapter, but I like to put things at different times. All right, so let's have a function that goes like this. Remember that function? Let's put some numbers in to make it easier to work with. I really only need to know what's occurring there. That's the most important piece. Okay? Do you remember this function? It was x squared when x was less than 1, and I think I did x plus 2, which, yes, makes sense for what I just wrote, when x is greater than or equal to 1. All right, good. So first thing I want to do, everyone, what's the value of the function at 1? 3. We agree? You can look at the graph and see it's 3 because that's where your closed circle is. And you can look at your the actual definition of the function. And you can see that it's 3. Everyone agree? 3. Let's talk limit now. What happens? What is the limit of f of x as x approaches 1? This case, it's going to be pretty important to look at both what's happening from the right and from the left. And I promise at some point I will get you a theorem about that. Yep, we'll have a theorem about this in a minute. So, okay. Well, where's it going from the left? In other words, if I approach 1 from the left, where is it headed towards? What's the value it's headed toward from the left? 1. Everybody see that? It's headed to 1. But if I approach from the right, what's it headed towards? Do you see we have a discrepancy in our left-handed limit and our right-handed limit? So now my question to you, and this will lead us to the next theorem, and then we will practice evaluating some limits. My question to you is, so that means, all right, forget the left side and the right side. What happens as you approach 1? What's the limit? Is it 1 or 3, or is it something else? Can you figure it out? I hope not. I can't. So what am I going to call it? That limit's undefined. So here's an example, and that's what I wanted to show you, where you can evaluate the function at a point, but the limit does not exist. Actually, that's what we use more often. DNE does not exist. So let me throw your first theorem at you. What do you think that first theorem is going to talk about? In order for a limit to exist, guess what has to happen? The right hand from the right side must equal from the left side. Does that make sense? So let's put that in formal theorem notation. And your first theorem is the relationship between one-sided and two-sided limits. So this is theorem 2.1. And let's assume f is defined, they all start the same way, for all x near a. We don't need to define at a. Remember that? We only need to define, f is defined for all x near a. Then the limit as x approaches a from f of x equals L if and only if. That's a biggie. The limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right equals L. That's your first big theorem. Assume. Yeah, so we all kind of start, let's assume f is defined for all x near some value a. They're kind of all going to start that way, okay? We can say the limit equals L if and only if the right-hand side equals the left-hand side. All right? And that's going to come part of how you're going to compute limits. So one of the methods is still in 2.1 and then the other methods are not. But there are basically 3 methods we're going to learn to compute. Well, there's only 3 methods to compute limits. All right. There are 3 methods to compute limits. First one, which is still part of 2.1, is numerically. Numerically. That's what we did last Thursday. We computed that instantaneous numerically. We just found a bunch of numbers close to it until we assumed, oh, it's got to be that. You're going to do that today. That's going to be your first lab problem. Numerically compute a limit. It's tedious. You're not going to do it often for that very reason. You'll see in a minute. We'll do one example, quick example together. It's tedious. Now, the quick, easy approach is graphically. That means you go in Desmos, put your limits in, just look at it, right? So the next one's graphically. Great way to double check yourself, right? You're doing the lab, even though you did another method, throw the graph in Desmos and does your picture match what you think it should be? Graphically is always nice. Problem is, yeah, I'm not giving you Desmos on a test, right? So you're not always going to have that technology to do it. So the third method, which we will cover in 2.3, is our favorite. No, it's not. Algebraically. Algebraically. We are going to go through methods, and that's what 2.3 is, to go through methods, how to use algebra to do our limits. Okay. So, numerically, number one. Let's do a nice, easy one, quick one. Well, not that it's easy. No, we're going to do one I already have the answers to, so we don't have to calculate too many computations. But get your calculators out, because you can do a little bit. We're not going to graph it. So, for example, 1. I want to look at the function I want to look at this function. Okay. Now, why do we need limits? We just saw that even though a function doesn't have a value at a certain point, it could still have a limit, correct? When you look at that function, where do you see an issue in that function? Well, there's a couple, but we're going to deal with one. The denominator. What's the issue in that? What can't I just plug in? I can't plug in a number 1. Does everybody see that? There's actually some other numbers I can't plug in, but we're not going to deal with that right now. Right? Because what's the square root of a negative? Anyway, you get the idea. We're only going to deal with the 1 now. Since I can't plug in a number 1, I'm kind of interested. I can't just plug in 1 and know where my graph is at 1, right? So I want to find the limit as x approaches 1 of the square root of x minus 1 over x minus 1. And I want to find it numerically. Again, I told you this is tedious. So to find it numerically, I need a table of values. Okay, and in the center of my table of values, so I'm going to put value there. I am going to attempt to figure out what's happening at 1. Okay? I don't know, because I can't plug it in. Now, we just learned, in order to find that limit, you got to go from the left and you got to go from the right. You can't just do half of it and just do one side, right? So what do I need? I need a couple values that are really, really close to it. I'm going to use for time's sake, the example in there as not a value that's really, really close to it. A little further away, but still close to it. All right. Does that make sense? And then on the other side, I might do something like okay. Do those values make sense? All right. I'm not going to make you do them all. You understand it would take a while, but try one because I want to make sure you all got your calculators with you. So let's plug in 0.9. So get your calculators out because I want to make sure, you know, the biggest mistakes on the test are not using your calculator correctly. So take a moment and tell me what happens. So the other thing is you need a lot of decimal places. So let's go with like 5 decimal places. Because to do this, we need some decimal places. So what do we get when you do 0.9 square root, take square root, subtract 1, and then divide that by 0.9 minus 1? And then 5 decimal places. Go for it. 0.51317. So again, make sure you are using correct order of operations. Take moments, even at home, to recalculate. Make sure you get that answer. If you're not getting it, you're just not using the right order of operations when you're plugging it into your calculator. And everybody's calculator is a little bit different in how they do it. Graphing calculators are really nice for plugging things in because you can see those parentheses you put around stuff. All right. So are we good with me just filling in the rest of the numbers? Do you want to sit here? You're going to do it on the lab. All right. I'm not going to make you sit and do it all now. So 0.99 looks like 0.5012. I really should use bigger print. It's okay. 0.999, 0.5013. What are we approaching, do you think, at this point? 0.5. Does everyone agree we're probably... But to get that, we got to look at it from the other side. All right? We have to look at it from the other side. So when I plug in 1.001, look at that. 0.499. Could be another 9 or an 8. Not 100% short there. Just going to put an 8. And then when I do 1.01, I get 0.498. So it's moving away, which is what we expected to do, 7.6. And then 1.1 is 0.488. So clearly, as we approach from this side and as we approach from the right-hand side, what is it going towards? Do you agree with that? Yeah. That's how you do it numerically. Okay? That's how you do it numerically. I'm going to stop this video because I want to go over the other techniques. What you can all do right now is if you have a graphing calculator, oh, it's going to be hard to plug that one into a graphing calculator. I was going to say, if you have Desmos, you got your computer, some of you, we do have computers there, plug it into Desmos and see what you get. Like I said, I love it on my phone. I just download the app. That's probably the best way. Plug it in. Look at the graph, because I'm going to hit stop and upload it real quick and then start a new video. So take a moment to try to graph that real quick. You have it in your notes, right? Square root of x. I can stop here.